All right, so what I want to do in this video is talk about subspaces of R2, and I want to think about what are all the subspaces of R2. And it turns out that there's a nice, neat way to categorize them all. And there's always two what are called trivial subspaces. The trivial subspaces are, there's always just the set with the zero vector. That's a weird vector space, but it's a vector space. You can add any two vectors in that space and you get another vector in that space. You can scale it by any real number and you get a vector in that space because any real number times the zero vector is the zero vector. And that's the subspace test. So that means that it's a subspace of R2. And again, it's a weird one. It's not a very interesting one. It's why we call it a trivial subspace, is that it's an example, but it's not very interesting. The other trivial example is R2 itself. Technically, R2 is a subset of itself. Whenever we say a subset, we just mean that it's a set that lies in the other set. So you have some set here, R2. So this is just like the previous picture that we had, and then we have some other set S. And by the way, S doesn't have to be a proper subset. It could be that S itself is this set. It's just some collection of elements of R2. Maybe it's the whole thing. Maybe it's all of R2, but it's got to be some subset. So that's also going to be a vector space. So this is always going to be true. The zero vector and the underlying vector space itself are both subspaces of any vector space V. So start with the vector space V, and the zero vector and the vector space V itself are both subspaces. So there's always two subspaces of a vector space, as long as we're starting with a non-trivial vector space. In R2, there's an additional type of vector space. So it turns out that any line through the origin, will also be a vector space. And so here the idea is pretty simple. What I mean by a line through the origin, and this takes a little bit of imagination here. So first of all, we can draw the line, but the way that I want to think about the line is I'm going to think about it as the collection of the points corresponding to the tips of the vectors. So we have some vector here, call it V, and when you put it tip to tail starting at the origin, whatever point the tip of the vector is at, I'm going to say that point is going to make the line. And then we could scale the vector, right? You can double it. You can multiply by -1/2, so that's going to make it half the length, but in the other direction. And when you think about all the points at the ends of these vectors, okay, when you scale the vectors, all those points are going to lie along the same line. That line will be a vector space. It'll be a subspace of R2. So any line through the origin is also going to be a subspace of R2. And again, it has all the properties that we need for a subspace. It passes the subspace test. If you add two vectors, think about what addition of vectors means in R2. So if I have two vectors, say I have a vector here, really just in general, if you think about adding two vectors, that means putting them tip to tail. And if you put a vector here and you add to it another vector, you're going to get another point on that line. So if you add two vectors, so let me get rid of the ugly picture here, but if you add two vectors along that line, you get another vector along that line because they're all in the same direction. And if you scale a vector V, you again get any vector along that line. And so it turns out that it passes the subspace test. So any line through the origin will turn out to be a subspace. Okay, so there's really three types of subspaces of R2. In R3, it turns out that there's going to be four types of subspaces. So subspaces of R3. Here, R3 is a lot trickier to visualize, but you have 3 dimensions. So you have an X, a Y, and a Z. And so there's going to now be 3 types of subspaces of R3. Okay, so let's just separate our work here. So there's going to be 3 types of subspaces. The first two are the trivial ones. There's, of course, the 0 vector, and there's the set R3 itself. No surprise there. Okay. Here, this is the 0 vector, and you can think of these axes as kind of extending. So the x-axis goes that way, the z-axis goes down, y-axis goes over there. And then you have kind of three-dimensional space. You can imagine kind of turning it and looking at a point in that space. There's going to be two other subspaces. It turns out any line through the origin, so any line through the origin in R3 being the point 0, 0, 0. Any line through that origin will be a subspace. Also, any plane through the origin will also be a subspace. Okay, these are a little bit less visual, but these are, turns out, are the only subspaces of R3. I want to emphasize, why does the line and why do the planes have to go through the origin? Think about, I think this might be easier to visualize in R2. Think about if you have R2, and then you're going to consider some line that's not through the origin. Why is that not a subspace? Well, building off the previous video, it's because it doesn't contain the 0 vector, right? The origin itself is missing. That means that the 0 vector in the underlying subspace R2 isn't in the subspace. And automatically, that means it's not a subspace. Okay, so this is not a subspace because it does not contain, so it does not have the 0 vector, which in R2 is 0, 0, or however you want to write the vector. Okay, so that turns out to be a key feature there. Okay, so here, if we have a line or a plane being a subspace, it's got to contain the origin. Okay, that turns out to be important.